So, you remember we spent some time talking about capillary pressure versus saturation curves and how those fit together with relative permeability versus saturation curves. They're kind of the essence of what we deal with. I would say the capillary pressure versus saturation curves are perhaps more important in what we're dealing with because it gives us some idea of the linkage between saturations and how those might vary in the subsurface. Good? Excellent. Yeah. And so we can use that to be able to say something about the distribution. So we spent last week talking a little bit about what those curves are. And I think it's perhaps useful to maybe recap that. So that's what I plan to do today, because it's a key component. And so I organized my thoughts so I could do this. I should plug this in, of course. How you doing? Good. And so this is kind of an amalgamation of a couple of figures that we've had. All right, so do this. So imagine that we have, we've done this split before. We have the water table, and we have material above this, so a free surface. And I'm going to draw this figure that we've done. I suppose I should be trying to be consistent with my units. So this is vertically. This is below the ground surface still, maybe. And if we draw a capillary pressure versus saturation curve above this, then if we don't do that, then we know exactly what that should look like, I think. We know that capillary pressure is equal to the non-wetting fluid minus the wetting fluid, by definition. And this is capillary pressure that we're plotting on the vertical scale. So this is PC. And it actually relates to the assignment you're doing now, actually, I think. And this is pressure, not capillary pressure, but it could be any of the different fluids that we talk about. Then we know that if we had, for instance, water, then the distribution is supposed to be blue, might not show up very blue. The distribution of pressure with depth would look like this. By definition, the water table would be at this level. And if this is 0, then are we using gauge or absolute pressures? Gauge, yeah. Excellent. Since this is blue for the, I'll do lighter blue, for the water, then if we look at the capillary pressure versus saturation curves, at least the one curve, this would be a drying curve, right? I haven't put a label on this, but I'm going to make this saturation of water between 0 and 1. Can't remember what the other colors were. Let's use red for any napple, dense napple. And if we do that, then the pressure versus depth curve will look like this. You can probably do a better straight line than me. It should be straight all the way through here. Do have an eraser. Oh, okay. Is that successful? What are the labels for this box? It would be dP dz is equal to unit weight divided by 1. So pressure would be, so this would be 1, and this would be unit weight of the non-wetting fluid. This would be 1, and this would be the unit weight of the wetting fluid. And green is going to be air. And so as we go up through here, air is basically the same as 1,000th the density of water. And so this is the green line here, which is air. Terrible, terrible. And so the reason for drawing it in this way is that if we now look in the vadose zone, and I guess I'm going to also do this backwards, not backwards, but also upside down. Again, pressure non-wetting minus pressure of wetting. Oh, this is masterful, isn't it? I can see you're impressed. So, vadose zone. So this is by definition the vadose zone here. So this is unsaturated above the water table. So this is the water table. We go up to the water table. There's no NAPL in the system. We're dealing with only two fluids. We're dealing with water, and we're dealing with air. So if we look at any particular height, it's kind of a height, but it's not really a height, right? So there's a bit of an incongruity here. Ignore that for the moment. If we look at the difference between these, then the non-wetting fluid is going to be the air, and the wetting fluid is going to be the water. This is zero pressure. This is positive pressure. This is negative pressure. Fluid pressure. And so if we look at the Capri pressure is this distance between these two. Green. So the non-wetting pressure is a big negative number. The non-wetting pressure is a small negative number. The wetting pressure is a large negative number. A negative gives a positive, so this is the difference between these two lines. The green line and the blue line is actually the Capri pressure. It's positive because of the sign convention here. And so in other words, if we figured out what PC is, and we figured out exactly what PC was here, remember that this is a pressure scale, this is a length scale, they're not the same, but we can map between them, and if we could map between them, then we'd end up with this line here. And we know that if that's the case, then this would be the saturation of water, and this would be the saturation of the non-wetting fluid, which in this case by definition is air. So it starts, so in other words, you know as you get further up the water table, originally it's fully saturated with water, you go up a bit, it's still fully saturated with water because it's the tension saturated zone. You keep on going up, you get progressively more and more air in the system, and the water becomes more and more scarce and less connected. So this is the mapping that does that. And I suppose the important thing to note is that the sign convention automatically takes care of this in terms of Capri pressures. And if you want, I guess I'd do this, just to remind ourselves, I guess we're already on the right figure. Remember this figure here. Gone too far. This. So this looks a bit like this. If you cut this off at mid-height, it's written in terms of percent saturation of oil, but this curve is, we're dealing with the upper portion of this air and oil, air and water together. The red is, ignore that. Yeah. Let's get back to this, because we're not thinking about oil right now. All right. So now let's go below the water table. So below the water table we have two fluids. We have the non-wetting fluid, which is now denser than water instead of being much less dense, which is this, which is maybe 1.6 times the density of water. And we have this. So if we take this and we draw this upside down, hopefully this is going to work out. And we do the same things. We take a particular height here. We have two fluids. We have a non-wetting fluid, which is the napple. We have the wetting fluid, which is still water. The napple pressure is a big positive number. The water pressure is a smaller positive number. And so the difference between those is capillary pressure. A big positive number minus a smaller positive number is a positive number. So capillary pressure is still positive. So this is still increasing capillary pressures. And this is also increasing capillary pressures from 0. So this line here is 0, and it's increasing both directions, kind of an unusual graph. And we do the same thing. We plot capillary pressure now to some magnitude. Let's say it's here. This is this new capillary pressure for the subsurface part. This is the saturation of water still. And this is the saturation of the non-wetting fluid. So that's kind of a simplification of the figures that we've seen. All it is this is turned upside down on itself. The things that we've done have been a bit more complicated than this, but this is the essence of it. We will talk today about defining heads as a function of what we'll refer to as matrix potential, which is P over unit weight of a fluid, water typically, plus elevation, plus, you recognize this expression. Certainly for soil water retention curves, there's no velocity, so this term is 0. In groundwater flow, the flow velocities are usually very small, and so this term just gets thrown away. So that when you talk about groundwater head in hydrology, these are the two terms you're dealing with only. No velocity term, no inertia in the system. In a portion of the groundwater hydrology domain, we'll refer to this particular term here, we'll talk about today, as so-called matrix potential. And so unit weight of water typically for air, water, saturated systems, and the fluid pressure actually in the water. It could be the capillary pressure, but it could be either. I mean, the reality is that because the pressure in the air is constant everywhere. It doesn't change because of the unit weight of air, so it's close to zero. It's both the pressure in the water and also the it's the pressure in the water. Otherwise, it doesn't work out. Right? If we were to plot pressure here, instead of pressure, we were to plot hydraulic head. And we also plotted that with depth. And we took our datum as z equals 0 here. What would that curve look like for these pressure curves? Easiest to do if you're going down. If you start here, what's the hydraulic head here? Elevation is 0. What's the pressure here in gauge? Gogh said it. Hard night last night. I won't throw chalk at you. This isn't grade school. And hey, I don't take it personally. So the pressure here is 0, elevation 0. Head has to be 0, right? What is the head at this point here? Elevation. What's the pressure? So it's pressure head, right? It's a swimming pool, no different. So you start in a swimming pool, you know that it's a 303 question. Everywhere in the swimming pool has exactly the same head. So the head at this point is this. So because down at this point, the elevation is negative z, the pressure is positive pressure. So the pressure has to be equal to positive. So if the pressure at this point is positive, this decreases by the same amount that this increases by, and so you're exactly on this line. So the distribution of head at this point would actually be a thick line that just is parallel to this. The head is constant. Just as if you go in a swimming pool, the head is constant. For every meter of elevation you lose, the pressure goes up by 1 meter equivalent weight of water, which is really what this term is. And so the head versus depth term looks like this. And so head is the useful parameter because it includes this elevation thing that is part of this. I've kind of lost my way on this. So this diagram here, I guess the point I wanted to make was that this diagram here is really this diagram. You have a portion which comes down here, where you have saturation of air going to here and saturation of water to the left of it. And here you have saturation. Are these the right colors? They're not the right colors, are they? Was air green? This is green. Water was blue. In the napple, then water is still blue. Do it here. Water is blue, and the napple is red. So this is the non-wetting. This is the wetting. This is the wetting. And this is the non-wetting. It's just that the non-wetting happens to be air in this case, and it happens to be an apple in this case. It has to be denser. And hopefully that looks like this figure that we have here. So that's the genesis of this figure, all kind of teased out, I think. So again, the non-wetting is air, the wetting is water, the non-wetting is napple, the wetting is water. It all comes out in the wash because of the definition of capillary pressures, which is this expression here. So these always end up being positive values of capillary pressures, as do these, and it's because, I guess, going from water to the non-wetting fluid, you're going in this direction here. Going from the water to the non-wetting fluid, I guess you're going in the same direction. I guess that's the reason. You can think about it. You're going from water to air, and it's this length. You're going from water to napple, and it's this length, and that's why these are always positive. So I guess the other thing that comes out of this is that if you drilled a hole in the ground and you measured at a couple of discrete locations what the pressures were at those two parts by using a piezometer, what would be the direction of flow that water would be moving in the aquifer? If you've taken 452, I bet you've talked about this. So if you drilled a hole to this depth here, you know the pressure is this magnitude, and you drilled a separate hole here, and the pressure is this magnitude. What's the flow? Can you calculate the flow velocity? You can, because you could use Darcy's law, of course. But we know that, for instance, Darcy's law is equal to hydraulic conductivity times the gradient of head, right? It has these other elevation terms if you do it in terms of pressure, right? So if you did it in terms of pressure, there'd be some other terms. But this is the easiest way to do it. Let's do it this. This is for flow in the vertical direction. What's the head gradient? dH/dz. Stop putting your hand up, just shout.
The differences between those 2 points divided by the distance between them.
Yeah, but that's in terms of pressure. So yeah, so that's what it is. So what is the magnitude of the head gradient? The head, I guess, at one point is equal to, at this point here, it's equal to this. And at this point here, it's equal to this. What's the change in head between those 2 points? 0. So by definition, this is 0. If this is 0, this is finite, the velocity can be 0. So it's the same as sitting in a swimming pool, for the same reasons. That if you're at the pressure gradient of the fluid at rest, then it really is at rest. So if it was water and the gradient had to be, your measured gradient in the water was now, I hope you can get out the door.
I hope I can.
Yeah, yeah.
No.
Really hard, like
To the right, clockwise to the right, hard.
I am 80 pounds. This dog probably weighs more than I do. I'm just gonna tell him that you tried locking me in.
You're trapped. Just take a seat.
Yeah.
But what about the back door? Back door works.
I seriously can't get it. Oh.
Good to see that chivalry is not dead. Good for you. Thanks. And so, what would the heads? Thank you. What would the head gradient be now? Well, without calculating what it is, you know that it would be probably here, and it would be here. This is dz. This is dh. If you want to be snippety, so what's the gradient? It's dh dz. This is positive. This is increasing in this direction, so I can't figure this out. This would be a positive gradient, right? This would be a negative gradient. So I think dh dz is negative. This actually has a negative sign there. So a negative times a negative gives a positive. So it'll give us a positive velocity. Z is positive upwards. So which is the direction of flow? Easy. So it all fits together. Hopefully it all fits together. Yeah, so that's a sign. But bottom line is, if you drill 2 boreholes, you measure the heads in those boreholes. If you find that the head is equal to the is vertical, is 0, head gradient is 0, then there can be no flow. If the head is larger, deeper, then it's flowing upwards. If it's the other way around over here, then it's flowing downwards. So you can immediately tell from looking at the pressure distribution exactly where the flow velocities would be. So this, I think, is an important figure. It relates to the assignment you're doing now also as well. And it really does link with exactly what was drawn here. Except you'll remember that last time that we're doing something a bit more difficult, that we're, in terms of the air-water system, we're also adding a little tongue of napple on the top of here, which would cause this to become a little lens, if you remember. This stuff here. And to be able to describe exactly what this was in terms of this is the water table, this is the lens that sits on the water table and slightly depresses the water table, and then this is the chimney above it, which has a relatively low saturation of the napple. So that's it. So that's, again, important concept. So if you have those, you can do a lot with the stuff that we talked about in this class. And it relates to this, and it relates to, I think, talking about how you'd think that the saturations would change with depth and how you would monitor for things. We talked about monitoring, but we didn't talk about how you would monitor. And so that's why I pulled this stuff up here, just for a bit of light relief. And so maybe certainly an entry-level job type thing is to go and take water levels in piezometers. And so how do you measure it? Typically, a couple of different ways. The most common is to use a water level meter, just a little sonde that has electrical cable attached to it, which is graduated in terms of length. You drop it down the hole and you reel it down. It has two conductors on it, so it's a flat piece of ribbon that has a conductor down each side, along with kind of length measurements on it. The little sonde at the bottom has a hole in it which lets water in, and it has an external sheathing with an internal cone, and they're electrically separated from each other. One is connected to the one conductor that goes up the ribbon. The exterior is connected to the other one. When it hits water, it bridges the gap between them, makes a circuit, and a light bulb comes on here, and you know that you've hit water. Some of them are able to distinguish between hitting napple interface and hitting a water napple interface, so you can get the interface between them. That's very, very straightforward technology. So you just drop it down the hole until the light goes on. You take the reading of how deep you are. You know where the water table is. The alternative, I guess, is to use something that could be left within the borehole. So you take a pressure transducer, you drop it down the borehole, you have the connections that come up to the top, and a data logger that may be downloaded by telemetry. And depending on the water level in the hole, it'll measure pressure, and that pressure gives you the water level. It goes up, the pressure goes up. Water level goes down, the water pressure goes down. If you look actually, I don't know if it does it at Spring Creek, but if you look at someplace along Spring Creek, you're talking about fly fishing, you see these galvanized, corrugated iron conduits, which are probably a foot in diameter and come out of the water of the creek and have a little box on the top. And so those may be either buoyant things in there that measure water level rises for the water level and telemetry back, or it could equally well be a pressure transducer sitting at some depth. Water goes into the casing, it fills it up higher, you measure the pressure, and immediately you get a water level that you can telemeter back to USGS for them to upload onto their website, which they then can also correlate with a flood stage with a flow rate. And if you're a boater and you want to go boating, you can find out what Spring Creek is flowing to see if you're going to scrape your boat and your butt along the riverbed or not, basically. So that's how you measure some of these things. Okay. All right. So that's kind of the big picture of this. It introduced one of the concepts that we'll need today, and that is the concept of matrix potential, which we've talked about. That allows us, which is really equivalent to capillary pressure at some level. I'm not going to talk about that. We know everything. This is just the same diagram, right? This part here and this part here are the two parts we just drew on top of each other for these two. So it's no different from that. But it's important to understand this and its nuances. So we're talking about, the title, I guess, was unsaturated flow. And so unsaturated flow relates to the part above the water table, to the vadose zone. All of the relationships that we've used for capillary pressure versus saturation and relative permeability rely on saturations in the water. And what we might explore today is two different forms of those relationships. We've kind of broached one of them, which is the Brooks-Corey, which are these log-log relationships. You'll recognize them in a moment. And we haven't talked about the Van Genuchten relationships. The Van Genuchten relationships are useful because they take capillary pressure versus saturation curves, and they give us empirical experimental values for typical curves, but they also allow us to get relative permeability versus saturation curves. So that's one useful thing that they do. And so we'll talk about those. Again, they're both a bit of a recipe, and we should never lose sight of the fact that the curves that we're talking about, the Brooks-Corey curves, are just a different way of plotting this top curve for water and air together. It's just a different way of plotting this. Okay? So this is the background for it. The idea is that we can take a capillary pressure curve that looks like this in terms of its components, capillary pressure versus saturation of water. And it looks like this. This is the drying curve. Oops. That's my arrow, which is a bit over-enthusiastic. We know that saturation of water goes between 0 and 1. We know that it has some fancy no-go regions, right, in terms of irreducible water saturation and the irreducible air saturation. We won't complicate it with those. We know that we could, for instance, adulterate this figure by plotting it in terms of saturation of water. We could plot it in terms of volumetric moisture content. The volume of water divided by the volume of the voids. So our definition is volumetric moisture content. MC. We know that when it's got no water in it, in terms of saturation, the volumetric moisture content must be 0. We know when it's 100% saturated. Do we know what the volumetric moisture content has to be, the upper limit? It's equal to the volume of the, this is total volume, sorry. So when the volume of water fills all the pore voids, so the volume of voids divided by the total volume is by definition porosity. So the upper limit for this is n or 0.3. So we could draw it like this. The same curve, it's just scaled with a different value. If we wanted to, we could cut this off at the irreducible saturation of water, as we've done before. And we could scale all of the saturations relative to that. We called this the effective saturation. Just by cutting this off, we talked about it at some length in class. So in other words, this value here is 0, and this value here now is 1. So we could choose a different scale. Likewise, we could do it for this volumetric moisture content. And if we did that, we could plot this as I'm going to use the same axes. We could plot it as effective saturation on the bottom, or log effective saturation. That goes between log of 0, I guess, is 1. And this is... no. It's not right, is it? So this, maybe this is 10 to the minus 4. And log of 1 is 1. Or 10 to the 0. So the same curve, just logs. If we do log of PC, then I think we get a curve that looks like a straight line. And so PC is 0 here. So it's 10 to the minus 4. And it's 10 to the 0, so it's getting larger as capillary pressures go up. And so this curve transforms into this curve if we plot it in logs. That's all, the only point I'm trying to make. And so where does this curve look? I think if you rotate this by 180 degrees, physically rotate it, not flip it, but rotate it by 180, then you get this here. And that's what this is. Only making that point. And so we can use our capillary pressure curves and relate them by a straight line relationship just by, one, plotting a different relationship in effective saturation, which the scale has changed from the irreducible saturation at 0 to 1, and then taking the log of that. Using the capillary pressure, and actually what it will usually be is the capillary pressure divided by unit weight of water, as we'll see in this. And taking the log of that, and we get a straight line curve. And this curve actually is just the red curve that we had before. And if we want to show it in the way that's normally shown, we just have to switch it through, rotate it through 2 quadrants, 180 degrees, and you get this. And so, if you like, I'm not sure it does us very much good. But if you like, we can look at the expression that defines that. It's this expression here. It was originally developed for soils, in which case the moisture content that the soil finds itself, whatever the saturation is, or the moisture content is, relative to the irreducible moisture content. Let's do these on these figures. So this would be the irreducible moisture content. This would be the saturated moisture content. Maybe I'll make it smaller so they both fit on. So this is the irreducible one, sigma W0. This is the saturated one, sigma S. And this is, again, the irreducible component. So in a physical sense, these two terms here, subtracted from each other, represents this full length. If you subtract this term onto the left-hand side, so you have theta minus theta W0, by taking this over here, right? Then this term here is just, if this is the volumetric moisture content you find yourself at, then this length here is just this left-hand term. So this term here, I'm not going to, this term is this term here. Perhaps you can't see that. The only point is that if you rearrange this, as you can, I suppose we could rearrange this as this term here. Theta minus theta W0, so these two terms gathered. Divide through both sides by this term. The saturated moisture content minus the irreducible moisture content is just going to be equal to this term here. Pressure we find ourselves divided by the bubbling pressure raised to some power. And I guess the point I was trying to make is that the ratio of this term to this term is just the ratio of this length to this length. So it's kind of a saturation, right? A relative saturation. When it equals 0, it means that you're at the irreducible saturation. When it equals 1, it means you're fully saturated with water. That's all. And so this is the Brooks-Corey relationship. We haven't called it, no, maybe we did call it that before, which is just this. If you take this relationship and you divide every single term on the left-hand side through by the saturation, volumetric moisture saturation when it's fully water saturated, then each of these terms individually become a saturation, right? Or an effective saturation. This is an effective saturation. It doesn't matter. I think I'm talking about things that perhaps don't matter so much to you. Bottom line is, we're able to get a relationship that allows us to map this curve onto this curve. It may seem a waste of time to get a curve that has a straight line relationship so easily defined as this, but actually it's not, because although we didn't really delve into it, you'll remember that we'd explained last time that when we talked about this mismatch between the depth of oil floating on a free surface of water that you measure in a borehole doesn't actually represent the true thickness in a borehole. The reason is because you set up a water table and an oil table, and by definition the water table has to be at atmospheric pressure. Oops, careful. And if we want to correct for this amount, to be able to do the calculations, we have to look at the influence of capillarity at this boundary. And one way to do this is to be able to look at the capillary pressure curves, which define the saturation of this. And one way to do that is basically to take these capillary pressure versus saturation curves in one convenient way that represents gasoline and air mixed together, two-phase fluids that have some capillary pressure curve, gasoline plus water mixed together that have a capillary pressure curve, and to combine it in some complicated way to be able to figure out exactly what a more sophisticated way of defining this behavior is that represents this true response that we have here. So that was our reason for doing it, even though we didn't ultimately use it, because we don't need it. And the same here is with Brooks-Corey, is that the reason for defining them by these straight line plots is that we can actually make this transition between the capillary pressure relationships that we've used here and these, a description of the terms. I think we said when we introduced it last time that all these curves represent are a straight line graph, y equals mc, or y equals mx plus c, the equation of a straight line, right? So this is y, this is the intercept, c, this is the gradient, so what's it going to be? M is going to be equal to y over c, so this is equal to m, this is equal to 1, this is the definition of the gradient. And so this is exactly this. If you counter it over on its side and you take this relationship, this is the relationship we get. Said that the ratio of these two things in a physical sense is just this length divided by this length. It's an effective saturation. And so what it does is it links an effective saturation with a ratio of two pressures. The pressure in the fluid and the pressure at which you push air into an otherwise saturated piece of core, and this. We can manipulate it. So we can take logs of both sides. If you log both sides, then you get this. Take a log of this, you get this exponent comes down here, and you take a log of these two. The log of two numbers divided by each other is the same as the log of those numbers individually subtracted from each other. And so this basically then becomes the equation of a straight line. It says that, basically says y is equal to minus m x. And the intercept is at 1, this value here. So that's all this term here is. And so if you look at physically what that means, since these are log components, this is one cycle. So log going from 1 to 10 gives you a value of 1. Difference between these also gives you a value of 1. And so this magnitude, so this value here is going to be equal to this is going to correspond to the y, which is effective saturation. So this is the effective saturation. So if we write this as y over x equals minus m over 1, just rearranging these components. This is the m, which is really the lambda. Then the lambda corresponds with y. Y is actually effective saturation, and so it's this limb of this gradient. The x are these two components here. You subtract them as you go across one log cycle in terms of pressure changes. So this, if this is 10 and this is 1, that's one log cycle, and that's equal to one log cycle here, because these are log terms, and you get the value of lambda. So, if you think about it, it's just the definition. It's nothing more than the definition of a gradient of a straight line and its intercept, but it happens to be in log versus log space. That's all. And if you use that, then we can use that to say something, and I think we talked about this before, and maybe we don't want to go into great detail, is if you plot these capillary pressure versus effective saturation or effective moisture content curves, then they look like this. And immediately you can correlate these magnitudes with the curves on the left-hand side. And I think you did it last time. Let's see if you can still remember. So out of these curves, this first one, this is pressure on the top, divided by unit weight of water. The lowest bubbling pressure is going to be the one that has the lowest air entry, which is going to be this one. The one that has the steepest gradient on it, that is closest to parallel with this line here, is the one that once you apply enough pressure to be able to push a bubble of air into the system, it's going to saturate all the other parts of the porous medium, so it's going to be very flat. So I'd guess that this one would be this one. Number 2 is this one, right? The most steep one here has to be this one here. I guess you could also rank them. If this is the one with the lowest entry pressure, it has to be this one. The one with the next lowest entry pressure has to be this one. Next one has to be this one. They're roughly the same. And the final one has to be this one, because they map with each other. And I suppose if we had a hard time, because these things look like they're the same location, if we wanted to figure out exactly which of these two ones were the true one, then I think we would settle on this almost vertical one as being the flatter one and being the one that represents this. So this has to be 2. So maybe seems esoteric as to why we do this, but the reason we do it is because of this calculation before about the capillary pressure versus saturation curves with depth and how to look at changes in saturations. Right. Okay, if I've confused you, this is the same rationale as before. We made the point that there are 2 of these curves that we might be interested in. The first is the Brooks-Corey curves, which we've spent some time working on, and the other ones which allow us to map between two parameters, not just to be able to get empirical values for these curves, but also to get the capillary pressure versus saturation curves, which we might want to have if we're going to look at rates of flow in the subsurface. So let's look at those. Again, they are representing a particular behavior. And so let's look at this in terms of what the recipe is. It really is a recipe. These happen to be the equations for the curves, written in terms of either an effective moisture content or an effective saturation as we've just defined. Before, the expression, I think, was something like effective saturation was equal to the pressure divided by a bubbling pressure to the power minus lambda. That was the expression. These happen to be written in a different way. It's just a curve fit, as indeed this was. It's just a realization that if you plot the log of the effective saturation and the log of the ratio of these curves, you end up with a straight line. That's the only realization is. So the Van Genuchten curves are just the realization that you can curve fit a capillary pressure versus saturation curve, drawn here a little bit differently from before, because this saturation is on a natural scale between 0 and 1, but this log of this capillary pressure divided by the unit weight, which is what we've called matrix potential, is actually written as a logarithmic scale. But having a logarithmic scale on this scale and a natural scale on this doesn't do so much. It maybe, I suppose, stretches in different parts and compresses the form of the curve, but it looks kind of like the curve we've had before, right? In general form. And it's really just a recipe. It's a recipe that relies on 3 parameters. One parameter, alpha, which is roughly equal to, I guess I'll do it as approximately equal to 1 over what we've called HC0. HC0. Remember when we drew capillary pressure versus saturation curves for saturation versus head? HC. The bubbling pressure was HC0. Then alpha is just the reciprocal of that height. So it's actually quite a useful parameter. Its units have to be in reciprocal length, so 1 over meters. And so if you know what the alpha value is for a particular soil, you immediately know what the bubbling pressure is. So actually, it anchors the curves at a particular location. And as you look down through this, we will find out that we can get values of alpha for a whole bunch of different soils just based on what the soil looks like. Clay, sand, silt. So quite useful. And the other two curve fitting parameters are these curve fitting parameters M and N. And they don't have any real physical meanings like this does. They're just curve fitting parameters. And so the bottom line is that if you know what these parameters are for M and N and for alpha, then you can make these curves, just like a levered curve, but for real soils. Maybe it feels a bit more real to you in that regard. And so you can always construct from these. And you can go to tables that for a silt, the values for these parameters should be 0.1, 7, and 22. I'm just making up numbers, but you can get numbers for it. So you can make these capillary pressure versus saturation curves to be able to do that. There is a procedure, and this stuff at the bottom just says exactly that. There is a procedure that if you had a curve that you measured or that you had, that you could then take that curve and you could figure out exactly what the value of M and alpha and N was. But I won't bore you with the details for that. It's just a recipe. It basically comes down to drawing the curve, figuring out what the residual saturation of water is, the residual saturation of air is, drawing some lines and calculating some numbers and figuring it out. So, but you won't be asked to do that, and I don't think we need to do that in this class, but you can do that. And the final component of this, which makes it kind of useful, is that we've said that you can get the values for these coefficients that depend on the particular value of the material that you have that your boots are standing on in the ground that's underneath you, and you'd like to know exactly what the properties of that are. And if you can get those, you can also use that to calculate relative permeabilities. And relative permeabilities, as you remember, are the kind of the other part of the equation. You know, these X curves. K sub r, and they look, depending on how you draw them, like this. This is water, 100% and 0. I guess based on this, this would be the water relative permeability curve, and this would be the non-wetting relative permeability curve. So Van Genuchten curves are for water, or the wetting fluid, not the non-wetting fluid. The reason for that is that the non-wetting relative permeability, the permeability of it is indexed by the viscosity. The viscosity of air, like its density, is very different from its the viscosity of water and air, not surprisingly, are very different from each other in the same order of magnitude as it is for the densities of water and air. So the density of water and air are 1,000 different from each other. 1 kilogram per cubic meter for air, 1,000 kilograms for water. I think for water, the viscosity is 10 to the minus 3 Pascal seconds, and for air, it's like 10 to the minus 5. So they're 2 orders of magnitude different from each other. And so the idea is that basically the permeability of the air phase doesn't matter. As soon as you blow in the air phase, it immediately feels it 10 feet away because it travels so quickly. So you don't care about it. It's always the same pressure. And so this is the relative permeability of water that you can get. You can define the relative permeability either as a function of saturation or as moisture content, which is what this term is here. And it is this term. It's a function of saturation. It's a function of saturation and these coefficients. If you define it in terms of heads, in terms of saturations, which might be useful, then again, magnitude of n, magnitude of alpha, and m. So all terms that you'd know. And so you could imagine that you could draw this relative pressure. So in other words, if you had a trace, for instance, that looked like this for effective saturation, it changes with capillary pressure. This vertical axis could also be in terms of a height of head that we calculate, which is this height here. And so all this is saying is that if you know what the capillary pressure curve versus saturation curve looks like, then maybe you can get relative permeability. Just because I feel like some variety, that looks like actually I think it might go up directly. This is effective saturation, but you get the idea. So it's this curve here. And so the idea is that you know this curve, you can define this curve by every single point, either as a function of effective saturation, or you could define it as a function of the head. That's what's here. And really all it's saying is that if you know how heads vary, it's probably easiest to think about it in this, right? We always think of these as effective saturation versus permeability curves. So if you just cycle through effective saturations from 0 to 1, so 0, 0.1, 0.2, 0.3, 0.4, then you end up with a relative permeability curve that satisfies each of these things. It'll look a bit different from that, but basically right here. If you cycled through magnitudes of heads that went up from 0 to 0.1 of a meter, 0.2 of a meter, 0.3, 4, 5, 1 meter, 1.5 meters, etc., you'd end up making the same curve, but I guess you'd end up with a relative permeability versus head curve. And because heads and effective saturations are uniquely linked through this, then you can always go backwards and forwards between them. So I guess a bit like in the example you're doing for homework, is that you can calculate the pressure versus saturation curve. Fine. It looks like this. Capillary pressure versus saturation curve. If you want to know what the saturation looks like as you go up in the soil profile or down the soil profile, you have to convert the capillary pressure to an elevation because of the height of water. So you're making that transformation. And so in making that transformation, all you're doing is you're linking this to be able to cycle between. If you wanted to, if you knew what the head or pressure distribution in the example that you're doing, you could also calculate, if you knew that at a particular elevation above the water table, that the capillary pressure was this amount, at some elevation z equals 4 meters, then I think you could also calculate, based on this, exactly what the relative permeability would, because of the relationship between these two figures. So I guess I'm just trying to explain the fact that you could calculate effective permeability, relative permeability, either by using saturation in the way that we've normally thought about it, but because saturations or heads are linked by this figure, you can also calculate effective saturation in terms of this term. And the final parting shot, as we use up the last couple of seconds, are that if you ever need to use these, this is basically the relationships for relative permeability curves. Let me make it larger. Relative permeability as a function either of saturation. I think theta effective is exactly the same. No, it's not the same. Or is proportional to effective saturation. You'll see that in these cases they're defined as a function of gamma. Gamma is not equal to unit weight of water. It's so in Fedder's book he uses M and N's to define these Van Genuchten parameters. In Van Genuchten's original paper, he's a Dutch guy, you might guess from the name, I guess. He used gamma and beta and alpha. Alpha keeps the same term, but this is a switch between them. And so you can calculate the magnitude of the relative permeability curves. You can calculate the magnitude of the effective saturation versus capillary pressure or head curves, the two curves we talked about. And you can do it directly for these individual materials. I guess this is the main take-home message, is if you have a material that you take into Klima's lab and you sieve it and you find that it satisfies the characteristics of a silt in terms of grain size, all of these divisions are based on grain size distribution, then you know that if the value of alpha should be equal to this, the value of beta should be equal to this. This is it's in units, it's not dimensionless, it's in reciprocal length. So if you know what each of these things are, you have alpha and beta. If you have alpha and beta, hopefully you can calculate gamma. I don't see it here, but you can. So you have alpha, you have beta from what we just looked at. You can calculate from that gamma. If you have gamma, then you have everything you need to be able to figure out all of these components here, which are the three parameters. Which means that if you find a soil on your boot and you track it back into where you work and you sieve it and you find out where it exists here, then immediately you can say something about the capillary pressure versus saturation curves and also the relative permeability curves. Unfortunately, I suppose you can't say much about the permeability, but I guess we did say last time that if we know that permeability could be written as, for instance, something like this. If you know the porosity and you know the diameter of the pores, and people often take the diameters of the grains as being similar to the diameter of the pores, then it allows you to get a magnitude of what the actual permeability is. And so if you want to know what the effective permeability is, it's going to be the actual permeability multiplied by the relative permeability, which is between 0 and 1. This is what Van Genuchten gives you. This is what hydraulic conductivity is equal to permeability over viscosity, density, and gravity. So you can always convert a permeability into hydraulic conductivity if you know grain size diameter. So immediately you have the effective permeability of your medium, essentially without having to do anything other than measure some things in a series of sieves.